Welcome back. This is section 2. We want to talk about electrophilic aromatic substitution of benzene rings to install a halogen, say bromine or chlorine. Now, as we've learned, we have a alkene that can react with bromine to give us the trans product here. And you can draw one of two enantiomers. And keep in mind that a nucleophile is defined as a substance with a lone pair of electrons or a pi bond. Okay, so the nucleophile here is the pi bond, okay? And so, it doesn't have a negative, it's really not delta minus, but remember that source of electrons in the pi bond are a little bit loose, they're more diffuse and further away from the nucleus of the carbon atoms, and they're available to attack something. Now the bromine atom here, as it approaches the alkene, becomes partially polarized, and we have a delta plus and delta minus, okay? But we don't need to worry too much about this polarization of bromine, which is a neutral, non-polar molecule just sitting by itself. But what's important to understand here is that this is the electrophile, okay? Okay, and this is the addition product here. We don't need to really talk about it. We're just going to move on to the aromatic substitution reactions. Okay, so benzene also has a lot of pi bonds, and so we would anticipate that this is the nucleophile because it has pi bonds. Now, we don't want to really talk about a carbon-carbon pi bond. We want to think about the whole pi cloud of the whole molecule, which we call a molecular orbital. And so that's the nucleophile. Now, it turns out that it's very, very weak. And so to enhance its nucleophilicity, we need to make the electrophile more attractive for the nucleophile. So bromine just isn't polar enough, okay? Bromine is a weak electrophile for this chemical reaction. So we need to activate it with iron tribromide, okay? Iron 3 bromide or iron tribromide. Now, bromine has lone pairs, okay? And this can attack, this is where we get into weird things with organometallic and transition metals and things like this, but basically don't worry too much about the charges of things. Well, worry about the charges, but don't worry too much about how many electrons does iron really have. And so if we draw a product here that we get, okay, this is an acid-base reaction. It was briefly covered in chapter 2 of your book, but this is a Lewis acid. Okay, this is the Lewis base. And this is the Lewis acid-base complex. And this substance here is much more activated. Now, if you look carefully, you can see now that there's a positive charge on that bromine on the right. Now, the bromine that's going to be attacked, so this whole thing right here is a good leaving group. That's one way to think about this, okay? This right here is a great leaving group, okay? This substance here is in equilibrium with very small amounts. And we'll make the leaving group leave. Bromine plus. Okay. I'm leaving lone pairs off here. I'm kind of being sloppy here, but that's on purpose. We don't need to focus too much about this. The point here is that I want to point out what the electrophile is. So if I may highlight this guy right here, that is the electrophile. So E plus is abbreviated for our electrophile. In this case, it's basically bromine plus, or bromine that's activated by iron 3 bromide. So you'll see some funky reagents used in this chapter, and the whole purpose is to activate the electrophile so that it's more attractive towards benzene, which is a very weak nucleophile. Okay, so in the electrophilic aromatic, well, before I talk too much about the electrophilic aromatic bromination, let me show you the general template or the general reaction you're going to see for electrophilic aromatic substitution mechanisms. Okay, in step 1 you make the electrophile, but we're just going to assume we have it. In step 1, what you're going to have is nucleophilic attack of your benzene onto at or towards the electrophile. Okay, and remember, the whole goal is to substitute that hydrogen for some group E. E could be a carbon atom, a bromine, chlorine, nitro, whatever. Okay, so in the first step, what we have here is attack, okay, of one of those pi bonds of the benzene ring onto the electrophile. Okay, and that's going to give us a complex, or a intermediate. Okay, and we're going to attach the electrophile in this reaction on the top carbon. We could have chosen the bottom, but we have to make a choice. And there's a positive charge now on the bottom carbon. Okay, so I just want to, before I show the second step, well, let me just show the second step. In the second step, what we have, so this is nucleophilic attack. You know how I like to abbreviate my individual curved arrow reaction mechanism steps by a letter. A stands for attack. Okay, and then what happens here is we're going to have a deprotonation. So let's go ahead and draw this in. Okay, now you might have sulfuric acid, you might have solvent, you might have methanol or some kind of protic solvent or something, or aprotic solvent usually. But anyways, the solvent is going to have some kind of lone pairs, and that's going to deprotonate this guy here. And the lone pairs are going to attack the proton, and then those electrons that made the carbon-hydrogen bond create the carbon-carbon pi bond. So what you get at the end of this is your benzene or aromatic ring regenerated, and you have the electrophile now at the position where it used to be the hydrogen. Okay, so let's just make a little note here. S quite literally is something, right? This can be solvent, it could be bromide, it could be lots of different things, as we'll see in this chemical reaction. Okay, now I want to discuss this intermediate right here. This intermediate looks like a secondary carbocation, but it's allylic, which means those double bonds next to the positive charge can involve in resonance. So let me show you the mechanistic details there for the resonance. Okay, now if you're asked to draw a curved arrow reaction mechanism for a process, this is all you need to draw with a real live E. Okay, it could be bromine or chlorine or other complexes and things. Okay, but the resonance is going to be used to describe how the intermediate is very stable. It's stabilized. So if we draw this carbocation here, I'll leave the H off there. I'm not going to draw H's really here, but this is it's looking like a carbocation, right? So we can use curved arrows here to show how these pi bonding electrons could be scooted over to the right. Okay, and that's going to also form a secondary carbocation that looks like that, right? And it's also still allylic. And then we could also move these pi electrons over 1 to give another resonance structure that has the positive charge on the top carbon, okay? Now, we need to know this when we're talking about selectivity. What you will want to notice here, and it's very important, critical to see this, is that the positive charge is at the ortho carbon, it's at the para carbon, and it's also at the other ortho carbon. Okay, so we'll see how substituents at those carbons that this positive charge appears to be located at might stabilize or destabilize a positive charge. So we'll use brackets here just to denote that those are all the same thing. It's all the same molecule, just different forms. So that really describes what's going on here with this carbocation, okay? It's resonance stabilized, okay? So let's go ahead and look at the electrophilic aromatic bromination here, okay? So here we are with the electrophilic aromatic bromination, and the reaction is going to look like this. We start with some aromatic. For now, we're just talking about benzene. And if we treat this with bromine and iron 3 bromide, okay, which is a catalyst, we need to use 1 mole of benzene, 1 mole of bromine, but we could just use 0.05 moles of iron 3 bromide, for example. So it's a catalyst. So remember, we put catalyst below the arrow. And what this is going to form is your brominated aromatic ring and possibly HBr. You're wondering, well, let's balance this chemical equation. And so I will. You're forming HBr. Now the iron bromide is a catalyst which just gets regenerated, so we don't need to really worry about this part of it, okay? So the curved arrow reaction mechanism in the beginning is always to make your electrophile. And I alluded to that earlier. Bromine has some lone pairs on each of these 2 atoms, and iron 3 bromide, it's really ionic, but I'm drawing these iron bromine bonds as covalent bonds. If that bothers you, that's fine. We're focusing here on the organic chemistry as much as we can. So here we're going to form our Lewis acid Lewis base complex. Now at equilibrium, you mostly have this molecule that I'm drawing right now. You don't have much or any at all of the Br+. So here we are with the electrophile. So that's equivalent to the electrophile, okay? Now what we have next is, let me switch to the next page here just to make sure it fits all on one page. So that's kind of step 1, create your electrophile. And that's a wild card, is different for all the different reactions, okay? Once you have the electrophile, then you follow those 2 steps that I proposed earlier. You have benzene, or an aromatic ring, and you want to attack your electrophile. And the electrophile can be quite weird and quite strange. So this is going to be your electrophile, okay? And so we'll use some arrows here. We'll draw the H in here so we can keep an eye on it. And we want to attack this guy. And that whole thing there is the leaving group, okay? So what do we form? We form a carbon-bromine bond. And I'll highlight my, whoops, I should have left that as a single bond. I'll highlight my hydrogen in yellow here so we can keep an eye on it, okay? Now after this step occurs, we do have this being ejected, which is technically our leaving group. And I just want to point out that this substance here is in equilibrium with FeBr3, which is the catalyst, okay, and bromide, okay. we're going to use bromide as our solvent, as our base to deprotonate in this next step. So this kind of illustrates how iron tribromide is rebirthed and it goes on to catalyze more of these events. Okay, you don't need to worry too much about that. This is the key step that you should focus in on, okay? Now, after we form that carbocation, yes, it's resonance stabilized. We don't need to draw all those resonance structures. What we do need to show is the deprotonation event. So we'll sketch in our carbocation here, and we'll highlight that yellow hydrogen here, and that's the one that's going to be deprotonated by bromide, okay? So bromide comes in, deprotonates, and these electrons move in to reform the aromatic ring. And so now you have bromobenzene, and this forms HBr. I won't draw that in, I'll just write minus HBr down below. So it evolves HBr in the chemical reaction. Those are the two fundamental steps there from the reaction, okay? So you create the electrophile, benzene is going to attack, and then something in solution is going to deprotonate. Now you just can't use hydroxide or some made up base. You've got to use what's present in your reaction mixture, okay? Now chlorine works in exactly the same way. I will just show you what that looks like here without going through the mechanism. But if you have benzene, for example, and we treat this with chlorine, now we want to use FeCl3 because we don't want bromine attacking or getting attacked. So we use FeCl3, and this gives us chlorobenzene, and you know, HCl would be evolved, right? So I'll balance this chemical equation here in case you're curious about that. All right, so there's a description of the you know, kind of activation energy here in the book, okay? And you can take a look at that at your leisure. I'm not going to go over that. The book talks about the bromination and it talks about the mechanism of the chlorination, but it's exactly the same, okay? If you do want to do iodination, I don't really focus on this personally in my classes, but in case your professor does, if you want to do iodination, there's a slightly different reagent that you use. And I find it interesting here that you have chlorine, you know, as part of the catalyst. But anyways, what you form here is iodobenzene, okay? And so again, the copper 2 chloride is going to be your catalyst that acts as a Lewis base. It's going to grab iodine, activate it, and then benzene is going to attack the iodide. So, you know, it's slightly different. So what you do need to memorize is the electrophilic aromatic chlorination and the electrophilic aromatic bromination, okay? So for now, we're just dealing with benzene. There's only one of 6 possible, you know, hydrogens that you could remove, and you're only going to get one product, okay? So now we'll just keep talking about all of these before we talk about synthesis and more interesting reactions, okay? Thanks for watching.